every single time you click a link, you're kicking off this incredible journey. A request zips across ocean floors, weaves through dozens of networks, and gets you a response in, well, less than a blink of an eye. Today, we're going to follow that one little click and find out how the internet really works.
So let's just start with this question. How is it possible that your click can cross an entire ocean in, say, 20 milliseconds? I mean, think about it. You hit enter on a web page, maybe you're in Seattle, and a server halfway across the world in Singapore responds to your laptop in a snap. What is actually going on in that tiny sliver of time? Well, the answer is this amazing mix of heavy-duty physical engineering, some really clever routing, and a bunch of super advanced protocols.
All right, let's get right into it. The first step in our little data packets journey is probably the most surprising one. It's not happening through the air. It's not wireless. No, it's happening in the very real physical world.
Yeah, this is probably the biggest myth about the internet. I mean, we all think about the cloud, right? Or Wi-Fi, or our mobile data. But the truth is, the internet isn't in the clouds. It's under the ocean. The global internet is a huge interconnected network of actual physical cables. It's really just a massive web of wires.
And when I say massive, I mean it. We're talking about more than 400 of these gigantic undersea fiber optic cables. These things are the absolute backbone of the entire global internet. They're the superhighways connecting all the continents. And get this, companies like Google own or co-own almost 20 of them just to handle their own traffic. That's how physical this is.
So, what's actually inside one of these cables? Well, it's pretty amazing. They're packed with these bundles of glass strands, and each one is thinner than a human hair. Your data, your click, that web request, it's not traveling as electricity. It's being converted into pulses of light, zipping through these glass tubes at incredible speeds. We're talking a single fiber carrying over 100 terabits per second. It's just mind-boggling.
So let's just hammer this point home. The most crucial thing to understand is that your request follows a real physical path. It starts as light leaving your device, it goes to your local internet provider's network, hops onto one of these massive backbone networks, shoots across an undersea highway, and finally hits a server farm that could be thousands and thousands of miles away.
Okay, so our data packet is now on this global superhighway. But how does it know which exit to take, right? There are tens of thousands of different routes it could go down, and there's no central traffic controller, no Waze or Google Maps for the internet.
Well, let's break it down. Inside a single network, think of it like your local ISP's network. There's a protocol called OSPF. It works kind of like a local town map. Every router knows the layout of its own little neighborhood, so it can find the fastest way to get around town. But that's just for local deliveries. What happens when you need to send a package across the country or across the world? You need something totally different.
And that's where BGP comes in. It stands for Border Gateway Protocol, and you can think of it as the internet's global postal service. It's fascinating how it works. Instead of every network having a complete map of the entire internet, which would be impossible, each network just announces to its neighbors, hey, just so you know, I can deliver mail to these specific addresses. And that's it. BGP is basically the glue of the internet, this trust-based system that connects thousands of independent networks into one single internet.
Now, this system is built on trust. And that's what makes this next part so wild. It shows you just how fragile that trust can be. A few years back, a simple mistake, a misconfiguration at Pakistan Telecom caused them to accidentally announce to the entire world, hey everyone, by the way, all of YouTube's traffic, yeah, send it to us now. And because BGP just trusts what it's told, networks all over the globe just did it. They started routing all their YouTube traffic to Pakistan where it just hit a dead end. Poof. YouTube was completely offline for the whole world for 2 hours, all because of one single bad announcement.
Okay, so our packet found the right highway system, it's heading to the right network. But there's still a problem. Even at the speed of light, sending data across the globe takes time. It creates lag. So the next piece of the puzzle is all about finding a shortcut. And that's where something called the edge of the network comes into play. That shortcut has a name. It's a Content Delivery Network, or a CDN. And the idea is really simple but brilliant. A CDN solves the speed problem by making sure your request doesn't have to travel all the way to the original server in, say, California. Instead, it stores copies or a cache of popular stuff like videos and images on servers that are placed all over the world, much closer to you.
So here's how that plays out. Let's say you go to watch a YouTube video. Your computer gets sent to the closest CDN server. Now, if that server already has the video you want saved on it, that's what we call a cache hit. boom, the video starts playing instantly. But if it doesn't have it, that's a cache miss. And in that case, the CDN server has to go grab the video from the original source, save a copy for the next person who asked for it, and then send it over to you.
And if you want to see this concept taken to its absolute extreme, look no further than Netflix. They built their own CDN called OpenConnect, and what they do is they literally ship big boxes full of servers, packed with their most popular shows, directly to internet service providers. They install them right inside the ISP's buildings. So when you're binge watching the latest hit show, that stream isn't coming from a server farm across the country, it's probably coming from a box just a few miles down the road.
Okay, so thanks to CDNs, the data is now physically close to you. We've solved the distance problem. But how that data is actually packaged up and sent over that last little bit of the connection, that's the final super critical piece of the puzzle to make everything feel totally seamless and instant.
For decades, the internet ran on a protocol called TCP, and you can think of it like a very polite but kind of slow conversation. It's like, hello to you. Are you ready? Yes, I'm ready. There are all these back and forth messages before any actual data can be sent. The modern protocol, which is called QUIC, is way more direct. It just starts sending the data on the very first message. It cuts out all of that initial handshake delay.
And this modern infrastructure, it operates at a scale that is just hard to even wrap your head around. Take a network like Cloudflare. On average, they process over 50 million legitimate requests every single second. That's only possible because of this super efficient combination of CDNs and fast protocols like QUIC.
And that huge scale isn't just about making things fast, it's also absolutely critical for security. Because during a big cyber attack like a DDoS attack, that traffic can suddenly spike from 50 million to over 300 million requests per second. This huge, modern, distributed network is basically the shield that stands in the way, filtering out all that bad traffic to keep the internet from just grinding to a complete halt.
So let's just do a quick recap of this incredible 4-step journey your click takes. Step 1, it travels as pulses of light through actual physical cables under the ocean. Step 2, it figures out where to go, navigating between thousands of networks using the BGP routing protocol. Step 3, it finds a shortcut, grabbing the content from a local CDN server near you. And finally, step 4, it gets delivered to your screen super efficiently and securely using a modern protocol like QUIC. All of that in a fraction of a second.
And here's the most amazing part. This whole unbelievably complex system works, and not because one company or one government is in charge. It works because thousands of totally independent networks all agree to cooperate with each other using open standards. There's no CEO with the internet. It is a global network built entirely on a foundation of mutual trust. And that leaves us with a final and pretty important question to think about. In a system that's so decentralized, who's actually responsible for protecting it?